Okay, so let's just recollect what we did last class. So last class we were looking for a compression algorithm for vertex cover. So what we were looking for is some sort of compression algorithm for vertex cover. So what was given in this, that we were given a k plus 1 size solution and wanted to find a solution of size at most k disjoint from the given solution. Okay, so to do that, what did we do? So our first algorithm was basically is that here it is, okay, and we said that okay, so suppose this is x of size k plus 1, and so yeah, so we were talking about disjoint. Then our one algorithm was that if you wanted to really get a disjoint solution from here, then what we did is that if you want disjoint and this is a vertex cover, then the disjoint solution will just pick the neighborhood of x, right? Now to get to this disjoint solution, we said, okay, if you are given any solution of size k plus 1, then one way is that you enumerate all independent sets in X that will survive, right, and take its neighborhood. Say Z, take its neighborhood. Okay. And the other one was that you enumerate only maximal independent set Z, right? And then we took enough. Then what did we do? If you recall correctly, enumerate only maximal independent set Z. And then basically I'm saying that this maximal independent set is not going into my solution, right? And then what we did is that we computed, looked at this maximal independent set, looked at its neighborhood, and computed minimum vertex cover in Z union what I call n star Z graph, right? And since it was a bipartite graph, we could compute minimum vertex cover in polynomial time, right? And what happened because of that? So if you recall correctly, then what we said that this is the combinatorial lemma we proved. Any n vertex graph has at most 3 to the power n by 3 number of maximal independent sets. Okay, and hence, what was our algorithm? So then our algorithm was basically enumerate this maximal independent sets, okay, and compute the rest in polytime, in p time, right? So we got first algorithm for vertex cover, right, which ran in time 3 to the power k to the power 3 n to the power big 1, which was like roughly 1.4 to the power 5 k n to the power big 1, right? So this is where more or less we were there at last time. Am I right? Okay. So is this the correct summary of what we did last time? Okay. So today, so what did we learn last time? So our basic idea or the basic departure was that the technique that we employed to upper bound maximal independent sets in a graph should be applied directly to the problem, right? So this is the key observation we had in the last lecture, okay? And we started to build some of the nice algorithms here, okay? So this is where, what was our idea? We said, okay, fine, this is a very good idea that, this is a very good idea that what we want to do is to directly apply this. And then for vertex covered, we had this nice idea that, look, here's a key idea for vertex covered. And what is the key idea? Any solution S either contains a vertex V or N of V, right? So this is our key idea, right? That for, look at any vertex V and look at its neighbors, right? Look at its neighbor. So we could, when we, either we can decide that V belongs to my solution, or if we decide V does not belong to my solution, then what I know, all its neighbors must belong to my solution. So in the other branch, I could do this and recurse. Just one second. Okay, is that fine? Is this fine with everybody, this observation? If yes, please put +1. Okay. Okay, so thanks. Okay, so I just want us to be together till here because we are just going to build over this idea much more in today's class. Okay, so then we said that here could be a template for an algorithm. What is one template? A template for a vertex cover algorithm is as follows. Template. Some base case, find a vertex of max degree, say V, find recursively a solution containing V. Okay, so this, and in this, I delete V and I set my parameter to k-1. And in other, find recursively a solution containing N of V. So closed neighborhood of V, but what is a drop in parameter? Is an open neighborhood. Am I right? So this is the base case which we had. Okay. And if you take this template, then we had that one trivial algorithm is while there is an edge, okay, while there is an edge, find E equal to UV, okay, and recursively branch on U, or rather, okay, that's not, okay. So what I said is that what could be one base case? One base case is, so let's write down base case 1. What is base case 1? If G is empty and K is greater than or equal to 0, return yes, right? If G is not empty and K is less than or equal to 0, return no, right? In this case, what happens? When you are branching, right? When you are branching, you are at least branching on a vertex which has some degree. Am I right? Right? So in this case, what happens? What is the recurrence that I can write it? I can definitely write a recurrence which says T of K is less than or equal to in one branch. So at least I'm branching on a vertex of degree 1, right? So now when I branch, right, say U and V, in one branch, U drops by 1. So my parameter has become T of K minus 1. In the other branch, I am deleting N of V. So my parameter drops by N of V. But it could be that U has degree 1. So all I can say that in other side also K drops by 1. Am I right? Is that fine? Okay. So with how many people this recurrence is fine? If this recurrence is fine, please put +1. Okay. Okay. And then all of you people tell me that this recurrence solves to something like 2 power k. Am I right? And one of the reasons why you say that this recurrence solves to 2 power k is following. You say, look at the tree of recursion that forms. Basically, you have k, right? In one branch, in either branch, k drops by 1, right? And then k drops by 1 again, and so on and so forth, so on and so forth, ultimately like 0, 0, 0, 0, 0. And because, notice, this is a tree with every vertex, internal vertex, every tree with a binary tree has more leaves than internal vertices. Are you aware of this fact? Right? So rather than focus on the how many recursion, so what does this implies? This implies that in fact, number of nodes in the recursion tree, and this is what I'm going to call recursion tree. Okay. Number of nodes in the recursion tree is less than or equal to 2 times number of leaves in the recursion tree. Okay, which implies that modulo big O, we can focus on bounding number of leaves. Is this fine with everybody? So what was my goal? My goal was to bound total number of nodes in the recursion tree. And now I am saying that look at this set of leaves. These leaves are more than the number of nodes in the internally, which means if I can upper bound the number of leaves of this recursion tree, then I can upper bound the number of nodes in the whole tree by 2 times the number of leaves, right? And modulo big O, it doesn't matter. Okay, is this concept fine with everybody? Yes, no.
Then modulo big O.
Look, suppose I bounded the number of leaves by 3 power k. Okay. So total number is 2 times 3 power k. So if I write mod big O of 3k, does it matter what constant is here?
Oh, no.
This is what I mean by modulo big O of notation. We can focus or we can concentrate on bounding the number of leaves rather than bounding the number of nodes in the tree itself. Okay, this is exactly what I mean. Is this fine with everybody? Yes, no?
Yes.
Okay, then please put +1. Let's follow our essential agreement. Okay. Okay. So this is why we always focus on bounding the number of leaves. Okay. Okay. Then we came up with this beautiful observation. Okay. What was an observation? Observation was the following. We can assume that when we recurse or when we branch, graph has a vertex of degree greater or equal to 3. Why? Because our observation was the following, is that what was our observation? Observation was if delta of G is at most 2, we can solve vertex cover in P10. Okay. So now, because of this observation, okay, our base case in the template will change. Algorithm remains the same. It's just the base case in the template change, right? Okay. So now we say, what is our base case? Our base case is if delta of G is at most 2, solve the problem in P10. Is this fine with everybody? Okay, excellent. So, okay. So now if I write a recurrence, the recurrence is governed by this. Okay. T of K is max over D greater than equal to 3. T of K minus 1 plus T of K minus D. Is this fine? Right? So think of this. So somehow we can show that this is less than equal to upper bounded by this. Right? Because imagine the search tree. Okay. Now today I wanted to tell you a combinatorial view of this search tree. Okay. Now what I mean by combinatorial view of search tree. Okay. So first, before I go there, I wanted to write a different recurrence first. So let's first write it down. T of K minus 1 plus T of K minus 2. Okay. And suppose T of 1 is 1 or 0. We all know what this solves to. Right? And I also taught you last time the best way to solve this recurrence, you guess that this recurrence solves to some x to the power k. So then by induction hypothesis, this is x power k minus 1 number of leaves, right? And then if you solve this, it is going to get x squared less than equal to x plus 1. And this is what, if you solve this recurrence, you will get this 1.61 to the power k. But I want to understand really combinatorially that this is exactly what it is. Can you do that? If I did not want to use recurrence, right? So for example, look at when I draw this picture, right? K minus 1, K minus 1. All of you can say, hey, what is the total number of nodes in this tree? It's like 2 power 0, 2 power 1, ... 2 power whatever, right? Right? And then you sum up this up. And because of our thing, we said, okay, ignore all this. Just worry about the last term. And then he said, hey, this is combinatorial 2 power k. Okay. Now, these recurrences are great. Okay. And they give you exact number. But at sometimes in algorithms, this is not good enough for our purposes. Okay, sometimes like these recurrences are part of a bigger object, and we need to know combinatorially what they mean, combinatorially what they are. Okay, so I want to go. Let's try to come up with a combinatorial proof of this fact. Okay, so what I mean by combinatorial proof, I would like to give a embedding or give a mapping from number of leaves to something and say, hey, this mapping is injective and hence things are nicer. Okay. Okay. So now let's try to see what do this means. Okay. Now this is something which like long time back I derived it for different reason, but let's see if I can. Okay. So imagine yourself that I had K. Okay. Now, what is the, if I solve recurrence, what is this? This is K minus 2. Okay. Now, again, what is this? K minus 2, and then this is what this will be?
K minus 3.
And what is this? Right? I want to understand, but still, I'm still doing branching into steps. Okay. Any other algorithm we will view differently when we get there. But now, okay. So now let's fix K equal to 5. Okay. And I want to follow this essential practices. And let's see what happens. So if I have 5, what happens? 4 and 3. Then what will happen? 3 and 2. 2, 1. Sorry, you're right. Okay. Okay. And maybe say when it comes 1, we just stop. Okay. Now 3 can go still further, right? What will 3 will become?
2, 1.
2, 1. Okay. What will 2 become?
1 and 0.
0, something like that. And what will 2 become? 1?
0.
Okay. So we'll stop at 1 and 0. Okay. So this will not go further. This will not go further. This will not go further. What will 2 go to? 1 and 0. This is exactly the whole tree I have drawn for you. Right? Is that, does this tree make sense to you? This is how things are dropping. Okay. Now, if I wanted to understand this tree, what I want to see. Okay. So there's something funky happening here. There's something fundamental happening here. Okay. Suppose when I go right, okay, what happens if I go right?
Decreasing by 2.
Okay, excellent. When I go left?
Decreasing by 1.
Excellent.
Again, same thing. 1.
Okay, I close my eyes. I say, hey, to get 1, I applied LRL operation. First I applied L, then I applied R, then I applied L. Then can you get that, what you did? So first your K dropped by 1. So you included some vertex in the solution. Then you did R, then you branched where you did not include some vertex in the solution, but you included its neighbor. So if I told you this sequence, you're done. Okay. Okay. So first let's ask. So I can have left, right, left, whatever, or I can have 0, 1. Up to you, choose. Right? If I meant 0 is like going left, right? And right going 1. I mean, like I can distinguish how much am I making a drop. Yes. Okay. Okay. Now, like, let me ask you, what are possible length of what are possible number of right operations can we make? Either you can do 0 right operation, or you can do 1 right operation, or you can do 2 right operation. Right? How many of them? I do not hear, Ajay. You are muted.
K minus 1. I mean, if you're stopping when we reach
Just
1.
right operation. How many times in any sequence, how many times can you apply right operation? K by 2. Exactly. Okay. 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 So now I'm going to write LR is this. So now every leaves can be identified by, okay. So now notice. Every leaf in my tree has a sequence of LR, right? Okay. So every leaf is identified by some LR sequence, right? Left, right, left, right, left, and you reach this node. Am I right? Okay. Now, what is LR? LR is some, okay, is like LR sequence where LR, like, or rather, let's say, LR is, say, leaf whose LR sequence has R's. Okay, how many R's? R's. Okay, so what is the cardinality of L? It's summation LR, R going from 0 to K by 2. Is this fine? Because these sequences are unique. You cannot have sequences with exact, you cannot have 2 leaves with the same sequence. Like it's an ordered sequence, like left, right, left, right, left, right, 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 left. Because if there are 2 different leaves from the root, their paths are distinct. So if their paths are distinct, then at some place they will be different. Is that fine?
Saket?
Hi Pallavi, tell me.
Yeah, so we also have LL type sequences or RR type sequences.
Yes, there is, no? Look at LK by 2. What is this sequence? You are going to apply right how many times?
K by 2.
So what is that sequence going to be? The R only, no?
It could, right. Right. Okay.
Okay, so LR is leaf where this sequence is applied, right? Right? Yeah. So if you look at this RRR, where this leaf will be captured? This leaf will be captured in LK by 2, right?
Right.
That's it.
Okay. R equal to 0 is all left.
All left. L. That's also captured, right? So you tell anything and I will tell you where it is. Because it's just that all I'm saying that this is all that it is. Is that fine?
Yeah. Okay.
Okay. This is very useful. This analysis is very useful when you cut your tree somewhere in between. You understand the point?
Not really.
Okay. So suppose you are doing a branching algorithm and I wanted to see that, look, in the root, in the leaf node, if the size is this, major is this, I will apply some algorithm, right? So if I just apply 1.618 to the power k, and then I have to take the maximum possible k in the leaf. But different leaves will leave different values of k based on how many times you have branched right or how many times you have branched left. Right? Okay. So we will see one of such examples at some point of time. Okay.
Can I interject? Just a question.
Yes.
So for LR, basically the sequence, the leaves are consisting or are like strings that which have exactly smaller number of capital R's.
Correct.
And there are basically
I have
R
no bound
plus
on
one
L.
gaps. Yeah, and there are R+1 gaps, basically the first, in between, and at the end, and that's where you can place the lefts.
No, Sushmita, I'm not saying anything. We will get there later. Okay. All I'm saying to you, look at your leaves.
No, just a minute. But then imagine LK by 2. So that would consist of all those leaves where exactly one left move happens.
No, I'm only talking with respect to right.
Yeah, but your definition said leaf whose LR sequence has R's, right?
Yes.
So, but
I'm not saying anything about lefts.
So
you can have unbounded number of left at this point of time, but you should only be applying R times R length, R sequence.
Yes,
like,
yes, that is fine. That is correct. That's okay. No, I'm just asking for a clarification. So these are the leaves where So just think about LK by 2. So those are the leaves which are reached by moving left exactly once, and all other times you move R.
So that will be like K by 2 or K by 2 minus 1, right?
Yes.
Look at your leaf. No, what you ask yourself: how many times have I applied R move in this? 0 times, 1 times, 2 times, or K by 2 times? Based on that, you classify them.
And how am I storing this leaf information as a string?
No. I'm just I have my algorithm does this. This is just a computation. This is just an upper bound on this number of leaves in this.
Yeah, that's fine. But I'm saying this set, right? L small r, this definition, how do you store the leaf? Isn't it the string sequence you had to follow?
No, I'm not storing anything. So this is just a definition. I want to give you an upper bound on the cardinality of L. Okay, let's move on. Okay. This is nothing to do with algorithm. Okay. I'm just trying to give a combinatorial upper bound on the number of leaves. Okay. All right. Right. So I'm telling you, look at a tree where this moves happens, and this is where I reach. How many such leaves are there, or how many of such objects are there? This is the realm I'm trying to explain. Just 1 second. Okay. So is that fine?
L is set of all leaves.
LR is
capital L is the set of all leaves.
Yes, capital L is set of all leaves. Okay. Okay. Now look at set of leaves, right? So, and every leaf I also, so what is my, okay. So what I'm saying, with every leaf, associate LR sequence. Okay. And because of the algorithm, this LR sequence of a leaf is unique. Okay, so this implies that there's a function from leaves to LR sequence. Okay, and this function F is injective. That's all that I did. Now I'm trying to upper bound the feasible LR sequence which is possible in which is possible in this algorithm or in this tree. Madhumita, you had a question. Ask.
For LR, when you are counting L, which is sum of all LRs for all R 0 to K by 2. So every LR captures is like there is a sequence where how can I put R many right operations, number of ways I can put R many right operations, right? Those
we will not
leads to the only count.
I'm not saying anything. I'm saying to you, look at your tree. Okay, here's my tree. Right now, what is a sequence that I associate with him? This one. It is just read out. Left, 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 left. Right? This is a function that associates L to this node.
Yeah.
Okay. And what will this, my function will associate to this node? L, 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 and then R. Okay. What is this going to associate to this? L, L, R. Okay. What is this going to associate to this? L, R, L. What is it going to associate to this? L, R, R. What is this going to associate to this node? R, L, L. So this is just a function that associate with leaf of my tree a sequence. And that is, you start traverse from the root to this leaf in this tree. Okay. And you just see whether you are making a left move or right move, whatever, and just write down that sequence as a name for this leaf. It's a name for this leaf. So every leaf I'm giving a name. Okay. So so what does my function f does? For each leaves, it associates a name. And what is the name? The name is the way I give a name is that look at my root. Let's read this. Let's read whether I'm going this side or that side, and whatever way I go coming to this leaf, that is my name. Okay. Is this clear to you?
Yeah.
Okay. Now A, if you look at this properly, you will see that names of any two leaves are distinct. They can never be same. Right? Look at the first term. Either look at any two leaves. Either they are distinguished at this because they are either this side or this side. Right? If they are this side, then at the first place itself they differ. One will get L, other will get R. Otherwise, you move that to the second. Okay, fine. Now either it is in this subtree or in this subtree. Then at the second place, their name will differ. If not, then you move to the, like ultimately there will be a common place where they move, one guy moves to the left and other guy moves to the right. And that is a place their names will differ. Right? So everybody has got a different name. Right? Which implies that my function, which for every leaf associate names, are injective because if I take any two different leaves, they get different names. Okay?
Yeah.
Now I want to upper bound the number of different names that I gave. Okay.
I just wanted to see that like there can be more than one paths in that recursion tree, which has same number of R's, right?
Look at this, no? Look at this. You find yourself. Look, I have drawn for you, right? Look at this.
The first two that.
Yeah, look at this. What is the name of this? It is LRL, right?
Yes. Yes.
Okay.
And the one that is LLLR.
Yeah, this. I mean, I'm sure you can find this. This is like it's not a big deal. I mean, let me check.
But we can like say that these codes are like prefix to
532. What is
54320?
Yeah, look at LLR, right? Look at this LLR, right? Look at name LLR, and it also uses only one R, no, two L's. Look at this. Look at this. LLR, right? So two L's, one R. Look at this, two L's and one R, but their names are different. One is LRL, other is one is LLR, other is LRL. That's it. And why? Where will they differ? Look at any two leaf. Look at their common ancestor, right? That is the place one guy goes left, other guys go right, and at that is the place their names will differ.
Yeah.
And that's it. So this mapping is indeed injective, right? So what did I do? I gave you a method to associate names, right? That's it. And I told you that two different people have got two different names. That's it. Okay. Is this clear to everybody? Like, because this is crux.
Yes.
Okay. Now what I want to do, okay? So now that we all have understood this, okay, excellent. Okay, so now I said, okay, now what is this? I have given names. So what is names? Names are element of LR stars, right? This is what it is. Names are consisting of, names are over two alphabets, L and R. That's what it is happening, right? Okay. So now I said, okay, let's classify these names based on how many R's are you using. That's it. Right? So what did I say? I said, what is LR? Names with R symbols of R used. That's it. So this is what it is. What is LR? All those names that uses R symbols of R. That's it. So now what is L? L is upper bounded by LR. And how many times can I use R? We can use R at most k by 2 times, because every time I use, right? Because everybody's length is like you are not allowed to have name more than k letter, right? K alphabet, right? Or the length of your name could be at most k. But if you use the letter R, you cannot use, your name has to be one shorter or something like that. Like each R is of value 2. Okay, so nobody can have a value more than k. And if you use R, you pay twice, right? You only have k rupees. So if you are going to use k by 2 R's, how much value you've already paid? Or you already have paid all your k's. That's it. Right? So this is what it is. Is this fine? Okay. 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 Now what I want to do, bound the size of Li. Okay, some Li. So what is the point of this? Right? If we use I times R, implies how many times are you going to use? How many times are you going to use L? Tell me.
K minus 2i.
Correct. So what is the length of this? So what is the length of this sequence? Length of the path or length of the sequence is k minus 2i plus I, because this is L, this is R.
Is it not k minus I by 2?
What do you mean by k minus I by 2?
The number of times L has to repeat. The number of times L can repeat in the sequence.
It's
Given
k minus
that
2i, no? Total is k. Right? And you are going to use I times how much? R. So, right? So we need to have k minus 2i times L plus 2 times I. So this is L and this is R, and this should be equal to k, right? Is that not correct?
Yes, it's the right hand side. You move basically pay twice. So I
Yes.
move to 2i. So
Yes. So this is exactly what I'm saying. So, Sriram, is it okay, or are you still confused?
I'm still confused. I still think it is k minus I by 2.
What is k? What length of the sequence?
No, not length of the sequence. The number of times L can repeat, given that I times R is repeating.
So if I times R is repeating, so
I by 2 is
wait.
2 times I is.
Wait.
Sure. I got it. Thanks.
Yeah. Look, Sutanu, okay? Imagine you have a budget of K, okay? You are going to use coin of 2i of them, because that is exactly what it means, that you have used R I times. So you already paid 2i. So how much is left? Is k minus 2i. So only that you can pay for the left, guys. Is that fine? Is that fine,
But
Sutanu?
why 2i, not I? We are using I times, so why it become 2i? That is confusing.
Look, your total budget is K.
Yes.
I'm asking you, how much budget is left if you use I hours for left?
K minus I.
But then what is the length? You have total money K rupees. Okay. You bought 8. Total money you have is 20 rupees. Okay. 20 rupees. Now you bought 4 pencils of 2 rupees each.
Oh, okay.
Okay. But you only bought 4 pencils of 2 rupees each. How much budget is left?
2 into 4. Okay. K minus 2 into 4.
That is exactly is K minus 2. I know. I bought R I times. Each time I paid 2.
But each time why we paid 2, that is not clear.
Because what is right? My budget drops by 2.
Oh, okay. Yes, got it. I forgot that.
Okay, so that's it. So, okay. So when a name or a string is in Li, its length is K minus 2i for left plus I times for right. Okay, so this is K minus I. Is that fine? Okay. Okay. So now I can ask you, how many strings of length K minus I is there that use I R? You tell me.
K by
I ask
2,
you. Huh?
K by 2 choose I into
Why K by choose I? The length of the string is K minus I.
Yeah, but we have to first choose like how many ways we can.
You just choose. This is the sequence
yeah.
is fixed. You just have to choose I times where my R is going to be placed. The rest is going to be filled anyway. So this is exactly upper bounded by this. So looking at the length of string K minus I, suppose this is my string, right? These are my locations, right? This is my K minus I locations. I have to choose which I locations R sits. That's it. So that is K minus I choose I. Is this fine with everybody?
Yes.
Really, everybody? Then put +1. Okay. I'm not doing any amazing maths at this point of time. Okay. But now, what is this? This is less than equal to summation Li, I going from 0 to K by 2. Agreed? Okay. So this is equal to less than equal to summation I equal to 0 to K by 2. Is this fine? Okay. All good? Okay. Okay. So now how to do this? Okay. So there are, how many terms are there? There are K by 2 terms are there. Okay. Look, it's literally, we are combinatorially counting everything. So of course we are going to, I'm only interested in upper bound. So there are, how many terms are there? K by 2 terms are there. Okay. Let I be the index for which the term is maximum. Okay. I don't know which one of them is, but suppose if I knew which coefficient, which this binomial coefficient is maximum, then the whole summation is upper bounded by K by choose time, say B is this maximum, right? Is that fine? Look, some one of them is maximum or maybe at most, right? They're just k by 2 terms. So if I knew which coefficient is maximum, it is just k by 2 times b. Is that fine? Yes, no.
Yes.
Right? Okay. Right? I don't know what this value is. So let's say for some I, okay, what is my b? Let's write it down. So b is equal to some say k minus I, choose I. Okay. Let's see how many of you. I want to upper bound this. There are many ways to do it, but let me say this is equal to 1 plus x, okay, to the power k minus I by x power I, okay, for this is true for any x greater than 0. B, this is less than this for any x greater than 0. Let's see how many of this. I don't know it, but this is less than this quantity is less than this quantity for any x greater than 0. Let's see if anybody figures this out. Okay. For any value of x greater than 0, up to you, you choose. Okay, this statement is true.
Yes, it is true.
Okay, then wait. Let's see. Other people should think for a couple of minutes. There is no one among all of you who does not know this. All of you know this. That's the only hint I will give you. Everybody of you know this.
Sorry, what was the question?
That k minus I, choose I, is less than equal to 1 plus x to the power k minus I divided by x to the power I for any x strictly greater than 0.
Yeah, it should follow from binomial expansion method.
Sushmita, you have to say this.
Sorry, I thought you were asking a question. I'm sorry.
No, I ask people if you know, like it's fine, but like.
Sorry.
Okay. Does everybody sees now? What is this? 1 plus x to the power n is equal to summation n choose j going from 0 to n, x power j. Is this fine? Right? So 1 plus x to the power n is greater than equal to n choose I, or rather is greater than equal to n choose L, x to the power L for all L between 0 to n. Is this fine? This is like total term is greater than equal to 1. And this is why I use the fact that x is greater than equal to 0. Otherwise, I can't say this. You get my point? So now this statement is true for anything. Okay, it sounds very simple, but the first time when at least I reached, I did not know this, or I knew this, but I did not apply this. But that time I knew maths. So if any of you know maths, if k minus 1 choose I is there, you can also get this exactly precise term by doing complex integration over some contour. I mean, you can get an upper bound on binomial coefficient by finding an appropriate contour to do complex integration. Okay, so check this out. I mean, if you want, I can send it to you using some residual calculus. But after doing all this, you realize that at the end, the term which you get is exactly this. So, like, you backtrack. But anyway.
We can also use You can also use like generating functions to get the closed form of this.
Yeah, but like, I do not want to use generating function. That's exactly my point, right? Okay. Okay, anyway, so we have this, okay? So now, what we have? So now we have very nice terms. Now we wanted to upper bound 1 plus x to the power I by x to the power I, right? Sorry, k minus I. Okay. So this is equal to, let's say, 1 plus x to the power k. Is that fine? Divided by am I right? This is exactly equal to. I have just did nothing. Okay. So I have, because x is greater than 0, there's absolutely nothing that I can do. If I wanted to minimize, so what is my goal? I want to upper bound this with as small function as possible. So if I wanted to minimize this, we choose x such that 1 over x plus 1x is less than equal to 1. Right? Because if this is less than equal to 1, then I know that whatever value for which this is less than equal to 1, at least for all those values, 1 plus x to the power k is an upper bound on this. Look, if I can show 1 by x into 1 plus x to the power I is at most 1, then what is it? Then I can show this term is less than equal to 1 plus x to the power k, because something is less than 1, right? Okay. Now, let's focus on 1 by x, 1 plus x to the power I is less than equal to I, if and only if 1x, 1 plus x is less than equal to 1. Right? Okay. Are you getting the same thing in the world? So what are we getting? We are getting x square plus x should be less than equal to 1 if and only if x square plus x minus 1 should be less than equal to 1. Okay. This is precisely what if you have done this, your generating function, this is exactly what you will get from binomial. This is exactly what you will get. So you find the roots of this equation. And then you will get 1.618.
So x squared plus x is greater than equal to.
Signs have switched.
Look at the
Sorry.
equation
So this will be less than equal to 0, right? See.
to the equation.
Oh, right. My bad. It should be this. Yeah. So this should be greater than equal to 0. That's it. Is this fine?
Yes.
Yes.
Yeah, that's it. So you choose x. Now you know how to solve your quadratic equation, no? And there was nothing that I did for 1, 2. If it was 1, 3 kind of branching, right, then you would have just gone back here, right? And I would have said, okay, fine. It's not k by 2, it's k by 3. Right? And so on and so forth, right? So whenever you have branching of 1, 3, 2, 3, you can do any of these things. But the moment it's like 3-way branch, 4-way branch, you can still do some of these things, but your alphabet will become much larger. It is no more just alphabet over 2, right? It will become left, right, center, right? Because whether you went, if you want, and you can still compute some of these things, but like it's way more tedious. My whole purpose was to just show you then like we can bound these things actually even combinatorially. I mean, it's It's nice. And you get exactly the same kind of things that you could have got from writing this recurrences. So one thing is proving inductively, and this is just a combinatorial proof, but it is exactly the same thing. Is this fine with everybody? Okay. Excellent. So we didn't talk about, okay, yet vertex cover, but that is exactly my point, was that just to show you that how these trees are and why these trees are nice and interesting. So from now onwards, I'm not going to do this much of detailed these things, but like it's good to keep these things in head. There are analyses where this is much useful to do than writing your recurrences. Okay, just one. Okay. So going back to our branching algorithm. Okay, so going back to our branching algorithm, what did we do? We said if delta of G is less than or equal to 2 p time. Okay, and this led to recurrence T of K is less than or equal to T of K minus 1 plus T of K minus 3, and this is x power K minus 1, x power K minus 3, right? So this should be x power 3 should be less than or equal to x squared plus 1. And how much this solves to? I think this is 1 comma 3, right? So I mean, I just use Mathematica, like Wolfram Alpha, and just put this recurrence and they will solve for you. Okay, but it is 1 comma 3. Okay, and this solves to, so why it is called 1 comma 3 branching? Because in one branch K drops by 1, in the other branch it drops by 3. So this solves to let me see, 1.4656, and hence the algorithm running time is this. And we made a better algorithm. Let's see, 3. No, it was 3 to the power 1 by 3. Okay, and we already had made an algorithm with running time 3 to the power 1 by 3, which is 1.443 to the power K. Right? So that algorithm that we made by enumerating maximal independent set was faster than the algorithm which we made. So now our question is, can we get an algorithm for vertex cover? Okay. Okay. Can we get an algorithm for vertex cover such that something nice can happen? Something is such that we achieve, say, less than or equal to 1.4 to the power. Okay. So what was the hurdle in this algorithm? The hurdle was that when we were trying to branch on degree 3 vertex, that is not nice. Okay, that automatically gives. So now what happens if we start adding something more to our algorithm? We say, okay, let's branch on vertex of degree at least 4 first. Okay, so if I branch on this, then branching algorithm in this will lead to a recurrence what? Right? So this is 1 comma 4 branching. You know what's the running time of this?
1.38, I think.
Correct. Okay, so this is like 1.38 something to the power k. Okay, now this is not fun. Okay, or rather say 1,48138 to the 3. Okay, so this seems to be a good number, but what I do not know how to handle when graph has a vertex of degree at most 3. So what we do not know, is how to do good or better when delta of G is at most 3, right? That's our hurdle at this point of time, right? Because we do not want to branch on a vertex of degree 3, right? So until I have a possibility of recursively trying to find a solution when a vertex has degree at least 4, we are doing very good. But when it becomes degree 3, so who knows? All we get is an input graph which has maximum degree at most 3. Right? It's possible, right? I mean, you never get to recursively try to find solution because there is no vertex of degree 4. So this good case never occur at all in my algorithm. How do I handle this? Okay. So here is something interesting or funky happens. Okay. Now look at a vertex. So now assume we have G with delta of G at most 3. And we want to find a good algorithm for this case. And then we will plug this algorithm into the general algorithm and get a good algorithm. So for now, let's assume that we are only trying to handle this. Okay. Now notice, here's a vertex V. So what is this graph? Has a maximum degree? How much? 3. So what happens when we branch on V? What is the branching means? V belongs to solution, or let's say X, Y, Z, or in other branch, X, Y, Z belongs to the solution. Okay. Now when V belongs to solution, what you do? You delete V. That's what you do, no? But then, okay, look at here. Let's make some observation. In G minus V, what is the degree of X? What is the degree of Y? Y, and what is the degree of Z?
At most 2.
At most 2. So imagine that one of them has degree 2, exactly degree 2 for now. Otherwise, we'll worry about some. So imagine that Y had degree 2. And suppose Y had both his neighbors had an edge. What could have done? Imagine the case where I branch V into solution, right? And then I find a vertex Y which has degree 2 such that its neighbors have an edge. What did we learn?
Yeah, use the degree 2 reduction.
So there's a degree 2 reduction rule which will tell that pick up this vertex into the solution, this vertex into the solution, and this is for free, right? Right? So in fact, here, after I deleted V, in fact, before I branch, K actually drops by 3 in this case, right? First, because you took V, but the moment you made a decision to take V, you are forced to pick these two guys. You are forced to pick these guys and this guy in this case. So before you make another branch, K has dropped by how much? 3. Okay, fine. You may be not so lucky, and Y has no edge. What did we do then?
Create a new vertex, merge these neighbors.
Okay, so what we did is that this is what we did, right? Which is called, this operation is actually called folding. What is this operation called? Folding, right? But then what did K drop by? What did K drop by? K dropped by 1 in this case, right? Because what was the reduction rule did? It folded, and whatever was the parameter, it dropped by 1, right? So what did we learn? So we learned that, look, when you are branching V into the solution, you can apply degree 2 rule and either drop your parameter by 1 or 2. Sure, this will definitely happen if you did generate a degree 2 vertex. Is this fine with everybody? Okay. So now our template should change, right? Okay. So what is our template? So our template is here. Okay. So I'll worry about template later. Okay. I started with a graph of maximum degree 3. Suppose that was my input. But when I fold, graph maybe not have a vertex of degree at most 3, no? I could fold because this has degree 2 and I put them, it could have degree 4. So I might have started with a graph with maximum degree at most 3, but by this operation, I may create a vertex whose degree is more than 3. Is it a bad thing or a good thing?
Good thing.
Yeah. But if I wanted to maintain an invariant that every time I have a vertex, like maximum degree of this graph is at most 3, then this is a bad thing, right? Which immediately implies that once you find this vertex, just branch. That's better for you. But I mean, so these are the kind of things that we need to worry about when we are designing an algorithm. That I might start an input with some property, but because of my operations, some of those property may be violated. So if I wanted to maintain those property, then I need to handle those anomalies in my algorithm or in my immediately. Like I shouldn't wait, because then the invariant of my algorithm might change. Okay. So for design of our algorithm, it's okay. Let's just do what we could do. Okay. We are anyway interested in designing an algorithm for vertex cover on general graph, not on maximum degree 3. So what could be our template? Some base cases, degree 1 reduction rule, right? If there's a vertex of degree 1, reduce. Degree 2 reduction rule, right? Am I right? Right? And then branch on maximum degree vertex. Okay. Now tell me what is the running time of this algorithm. Now I will not tell. I wrote down the whole algorithm. I have some base cases. Base cases means, oh, k is less than 0 and graph has edge. Say no. Oh, k is more than, like those kind of base cases. And then what I do, I apply a degree 1 reduction. If there is a vertex of degree 1, pick its neighbor, drop k by 1. Degree 2 reduction rule. Oh, if there is a vertex of degree 2, if it has a triangle, okay, if it has a, then put those two vertices in the graph, drop k by 2, right? Oh, if it is not, then apply folding, okay? So what is this? Triangle rule or folding. This is exactly what it is. So whenever you are able to apply degree 2 reduction rule, k will definitely drop by 1. Then degree 1 reduction rule, k drops by 1. So these are amazing reduction rule, because without doing any branching, they give you. So other way of thinking of reduction rule is, it's a branching rule with What is it? With one child. Reduction rule is nothing but a branching rule with one child. So I don't differentiate between branching rules and reduction rule. Okay, so what is a reduction rule? It's a special kind of branching rule where there's only one child, and that's okay. Because, and now you can say, but then how are you going to bound the number of leaves? Well, they are like a path. At most, k times something going to happen. Just short circuit them. Who cares? You get my point? Because k is it's great. I mean, all I'm trying to tell you that once you are well versed with difficult thing, these simple things you can gradually put it into your algorithm, right? But if you don't want to think in those directions, don't. But what is a reduction rule? So reduction rules are branching rules with one child or with at most one child. I really want you to analyze this algorithm now. I have written down this algorithm. I have explained you what this algorithm will do. First thing, when an algorithm reaches here, what is the branch on what is the maximum degree you will definitely be having in the graph? Anybody? They are definitely going to branch on a vertex of degree at least how much?
3.
Exactly. Excellent. Okay. So all of you people said that if we are able to branch on a vertex of degree greater or equal to 4, then that's great, because this leads to recurrence t of k minus 1 plus t of k minus 4. Okay, so let's not worry about it. Okay, but imagine branching on a vertex of degree 3. If this is the case, what is the property of graph G? What is the property of this graph G? If you're branching on a vertex of degree 3, it has no vertex of degree 1, it has no vertex of degree 2, it has no vertex of degree 4. So what is this graph?
Cubic.
It's a 3 regular graph. Right? Now this is why in branching algorithm, generally regular structures are hard to manage. Okay, so this is 3 regular graph, which implies if you delete a vertex, what are they going to get? At least one vertex of degree 2.
Yeah.
Like, I mean, because we are in the 3 regular graph, if you are going to branch on a vertex, any vertex we are going to delete, you are going to get at least 3 vertex of degree 2. It means you will definitely apply folding once, which implies in this case, k drops by how much?
It will ultimately drop by 2.
Yeah.
Exactly. Because once you deleted, and then you will be able to apply what? One of these 2 rules, right? Degree 2 reduction rule will apply. So because of 3 regular, when we delete V, when we delete V, we will at least have one vertex of degree 2 on which we can apply folding and drop the parameter k by 1 more, resulting in, so in this case, K drops by how much? 2. And in this case, this drops by K minus 3. So what is the recurrence here? Anybody? This should be very good. What is this?
It's 1.3247 something like that.
This will solve to, right? Now, so one recurrence, this solves to how much? 1.3803 to the power K, right? So I'm saying in my algorithm, either I'm branching with this recurrence or I'm branching with this recurrence, right? In the worst case, I might be branching with the top recurrence. So what is the running time of this algorithm? The running time of this algorithm is given by okay.
Oh, why not 1.3248? Why this or that?
Who said this? Sonak?
Yes.
Imagine yourself that you are always branching on a vertex of degree 4. Always. You never reach the second grade case. Right? So because we are talking about worst case complexity. So in the worst case, you might be applying the branching, the recurrence, which gives me the worst, gives me the bad. Okay. So now if I wanted to further improve this, what should I be doing? We have done great with degree 3, it seems. Okay. So the moment a graph has a degree 3 vertex, we are doing great. Okay. So now if I wanted to improve this algorithm, where should I be looking at? 1,4 doesn't look like we can't branch on, like if we just branch on a degree 4 vertex, it is not fun. It's not giving us enough. Right?
So we can do like this previous thing that we have done, like optimize this thing with n choose k.
Meaning?
On some values of k, use this algorithm, and on some values of k, use the n choose k subset algorithm, and optimize that thing.
No.
It will.
No, we are not trying. Our parameter is not number of vertices. Our parameter is k. What is n choose k means in this world? You mean 2k choose k?
No, k can be like any subset of vertices.
Yeah, so that is n choose k, right?
Yeah.
So this running time of this algorithm is just in terms of solution size. This running time of the algorithm is not in terms of number of vertices.
Oh, yeah.
All right. So there are major difference. Right. So we are still trying to reach the running time. Okay. So if I wanted to, so how do I decide how to further improve this algorithm? So now how do I go about? I go about and look at the recurrence, which is the hindrance or which is the reason why this algorithm is slow. Why is this algorithm slow? It is slow because of this recurrence. Am I right? So somehow when this situation arises, either I have to say that something more interesting happens or find some other clever observation which allows us to eliminate this recurrence. Okay. So how to improve? So how generally people go about improving it? Okay. Apply more combinatorial observation to eliminate hard case or case corresponding to recurrence with worst case running time. Okay, so for us, the worst case is, look at this. Okay, our worst case is when we are branching on 1,4. Okay, so now if we are just, so what will I do? Okay, if there's a vertex of degree 5, that's great for us. Okay, so let's just focus on graph of degree at most 4. And suppose I somehow give you that, look, you always have a graph of degree at most 4, but there is always a vertex of degree 3. Okay, imagine if I told you, okay, what did I told you? What is an invariant? Invariant is, I have a graph G, maximum degrees at most 4, and there exists a vertex of degree at most 3. Suppose I gave you this invariant. So first of all, if there's a vertex of degree at most 3, suppose there's a vertex of degree 2, I know how to do something. If there is a vertex of degree 1, I still know what to do something. Okay, but what I don't know, when graph has every vertex has degree either 3 or 4, and now I have this degree 3 vertex. Okay, here. Yeah, this is a degree 3 vertex, right? Now, what could happen? Either had, suppose this is U and this is X, Y, and Z. Imagine that all X, Y, Z are of degree at most 3, or degree at or equal to 3. Then can I do something? Can I do in this case something? If I delete U, then at least one of them will become degree 2, because X, Y, Z has degree 3, and I can do something great. Okay, fine. So it's not the case. Okay, if it is not the case, and suppose there is a vertex Z of degree 4, what happens if I branch on degrees 4 vertex? If I branch on Z, what happens to U?
It will become degree 2.
Yeah, then I can fold. So, okay, so if I had this nice invariant, which I could maintain throughout my algorithm, then I'm doing some of the great things. But the question is how to ensure that there is always a vertex of degree at most 3. And whenever I'm branching, folding this and that, that invariant is maintained. Okay. So this is what we will try to see on Thursday morning class. Okay. And we will get an algorithm with running time roughly 1.32 or something. Okay. But here's the hint. Can you come up with, so like think about, look, I did not do anything. So it's a very good training for yourself to improve this algorithm by some of these ideas which we talked about. So can I branch in a way that things can fold? I mean, play around. It's a fun game. It's like a fun game, and just try. It becomes boring only after you have done for a few years, but not in the beginning. It's very fun because all of us can make some of these algorithms. Okay. So the exercise is until Thursday morning, try to improve this algorithm. Like try to beat 1.38. I would be happy if you come up with any number below 1.38. Okay. Okay. Otherwise, I will anyway tell you on Thursday, but it would be nice if you would have gone through this and thought for yourself. I mean, and this is like a public exercise. It does not have to be a private exercise. Like you can discuss and do, like, it's perfectly fine. It's not a private exercise. It's like, please discuss. That's perfectly fine. Try to try to think about this algorithm, try to think about some of the terminology, and try to come with a better algorithm than this. Okay, so it's a group exercise. Okay, I would be happy if you on Thursday some of you teach me this algorithm. Okay, but please don't look at internet or something.
When do we have to submit?
What, Prateek?
About the aspect that you had given the cheats. So, yeah, the cheats. So, the things in the cheats that you had given. So, when do we have to submit that?
Yeah, so let's discuss about this. Four of us, we can set a small little deadline for giving me some of these things, right? Is that okay, Prateek? Like based on your convenience, we all can meet together and just find like, okay, like concrete set of questions. If you want, we can discuss and say, hey, maybe take a week for this, take 2 weeks for those. Will that be okay?
Yes, sir.
Okay, Prateek, then let's try to meet on Thursday after my class, if you're free, for 10-15 minutes and try to discuss some of these things. Okay, so for now, Prateek, here's an exercise. Okay, so my first exercise, okay, so let's do given your problem, come up with an assignment sheet for yourself. That's your first exercise. So that's your first assignment is based on whatever I have taught you, come up with an assignment sheet for yourself. Okay, so that's a first assignment, to come up with an assignment sheet for yourself for your problem. And give me that in a week. Does that sound like a good plan?
All four of us?
Yeah, I mean, you want to discuss among yourself, I'm also perfectly fine with, but
yeah, we have different questions, but yeah,
but you are free to discuss. Yes, please go ahead and discuss, but make a questions for yourself. I do not want answers. Okay, so your first assignment is how good questions are you able to come up with.
Got it.
Okay, so you get a week for that. Okay, anything else?
Can I ask one question?
Sure.
So you have written that the case in the right, you have written maximum degree is at most k, and then in the second point you have written there exists a vertex of degree at most 3.
It's 4, not k.
No, yeah, it's 4, and in the second point you have written there exists a vertex of degree at most 3. So why this has to be true? It can happen that all the vertices have degree 4. Like what about like?
Yeah, it can happen.
Then we have to take care of that case as well.
Okay, yeah, of course you have to take care of case. Okay, so suppose you come up with a graph G. First time you get such graph, or suppose this, I pick up an edge UV. Okay, I pick up an edge UV. X, Y. Okay, I subdivide this edge twice. Okay, now show to yourself G comma K is a yes instance if and only if G prime comma K plus 1 is a yes instance. Check for yourself. This is a very well-known gadget for Vertex cover. I subdivided twice. Okay, now this graph has a vertex of degree 2, no? So I wrote degree at most 3, right? And okay, if you're careful enough in your algorithm, you can make sure that now I never change. Like I always am able to maintain an invariant that there is a vertex of degree at most 3.
Okay.
So yeah, in the beginning, but then I artificially create such an object, and now have fun.
Also, like if all the vertices having degree 4, then after removing
then only
one,
this is the case, right? So then only Saket says that we subdivide it twice.
You pick up one edge, Sonak, subdivide it twice. Now, what is this graph? It has a vertex of degree at most 2.
Yeah.
And hence at most 3.
So it falls into that case. Yeah.
Of course, I will increase the parameter by 1, k plus 1.
Yeah.
But I'm trying to tell you, you don't have to apply this operation anymore. You can make sure that in your algorithm, this invariant is maintained. If some vertex becomes very big, do something, branch immediately or do something, I don't know.
Yeah, but I'm like telling, like, if every vertex has degree 4, even after removing one vertex of degree 4, it will like become like 3 degenerate.
Yes.
Like, there won't be.
Yeah, so that is one way.
Only
so
one time have to do.
Yeah, that's right.
But here the invariant is different. Is that the one that
that's okay.
Saket
So
has
what?
written?
Yeah. So what he's saying is that you could just say that, okay, in the beginning it's not the case, but we branch once, okay, and then we have this invariant, and then we never will, right? Because either you take this vertex, then also there are enough vertex of this kind. If you take its neighbors, you still have a vertex of this kind, because you have no vertex of degree at most 5 or more. Okay, so it's fun, and this is exactly what I'm saying. Trust me, if you guys sit down and spend some time on board, you will be able to get an output. Like, yeah, I've given enough hint, and if not, I will do. Okay. Then see you on Thursday. Okay, bye. I will upload the videos now. Okay, bye.
So tomorrow, no class.
No, tomorrow there's no class. I mean, that's all that I wanted.
Lecture note.
Huh? I'll forward this. I'll put that in the folder now. Okay. Yeah, that the whole reason of teaching now is not to teach tomorrow. No? Okay, bye.